In this video, we're going to prove the alternating series test. And it says, suppose that you have a bunch of numbers, a1, a2, a3, etc., with a1 greater than or equal to a2, which is greater than or equal to a3, and so on. And all these numbers are positive. And suppose that the numbers approach 0. Then the alternating sum, the sum from I equals 1 to infinity of -1 to the I plus 1 AI converges. So the idea is that you have some number 0, well you have 0 on the number line, and then you have a1, which is some positive number, and then you subtract a2. So a2 is less than or equal to a1, so you might be at 0, but you might be, say here, that's a1 minus a2. And then you add a3, so maybe you're here. And then you subtract a4, so you get here, say, and then you keep going back and forth, except with the distance approaching 0, the amount that you move right or left approaches 0, and then the series converges. Okay, so that's basically the idea. It's just going to go back and forth, and then it's going to converge. So how do we prove that it converges? Well, first, let's prove a little lemma that will be useful, which is, suppose that you have n and m being positive integers with n greater than m, then a sub m minus 1 minus a sub m plus 2 plus dot 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 plus a sub n minus 1. Well, you don't know if it's going to be plus or minus, but it's going to be plus or minus whichever one it is. A sub n is less than or equal to a sub m plus 1. Oh, that should be an a plus. A sub m plus 1. Okay. And the reason why I'm using m plus 1 and n is because we're going to try to prove that this series, the sequence of partial sums, is a Cauchy sequence. And then that will prove that the series converges. So, okay, why is this true? Well, I mean, intuitively, it kind of makes sense what's going on. So you have a sub m plus 1 here, and then you subtract, and then you know, so you're subtracting, you're moving to the left, and then when you're adding a sub m plus 3, you're moving, to the right, but then by less. So then you should be less than a sub m plus 1, which was your starting number, unless they were sort of the same, and then you ended up going back, right? So if a sub m plus 3 was the same as a sub n plus 2, then of course it would be back at a sub n plus 1. I mean, that's basically the idea. And so hopefully it's believable, right, that this is true, right? So we're using the fact that the AIs are positive, and that they're decreasing. But let's just write out more detail. So let's just look at a sub m plus 1 minus a sub m plus 2. Well, since you're subtracting a non-negative number, that's certainly less than or equal to a sub m plus 1. And then a sub m plus 1 minus a sub m plus 2 plus a sub m plus 3, you can write that as a sub m plus 1 minus parentheses a sub m plus 2 minus a sub m plus 3. And you know that a sub m plus 2 is greater than or equal to a sub m plus 3, so then this is less than or equal to a sub m plus 1. And then for the next one, a sub m plus 1 minus a sub m plus 2 plus a sub m plus 3 minus a sub m plus 4, well, this is less than or equal to this previous term, right? So, I wonder if I can just move the whole thing. Let's see. yeah, this is very annoying. Well, okay, I'll just rewrite this. Plus a sub n plus 3, which we know is less than or equal to a sub n plus 1, right? So, and then what happens if we keep going? A sub n plus 1 minus a sub n plus 2 plus a sub n plus 3 minus a sub n plus 4 plus a sub n plus 5. Well, we can compare this to the previous sum here, because this is going to be equal to a sub n plus 1 minus a sub n plus 2 plus a sub n plus 3 minus parentheses a sub n plus 4 minus a sub n plus 5, right? And so if you keep going, you can see that this is going to be less than or equal to a sub n plus 1 minus a sub n plus 2 plus a sub n plus 3, and then we showed already that this is less than or equal to a sub n plus 1, and so on. So that's the proof. If you wanted to be super rigorous, you could prove it by induction, but yeah. Okay? I mean, it proves something that's pretty obvious. Anyway. So now we can go back to the proof of the theorem. Well, we want to show that the partial sums of the series converge. So we're just going to use a notation. So proof of the theorem. So let's just let S sub n be the nth partial sum. So that's the sum from I equals 1 to n of negative 1 to the I plus 1 a sub I. And we let epsilon be greater than 0. So we know that since R is complete, it's to show that the sequence of partial sums converges, it's enough to show that it's Cauchy. So we want to show, so it suffices to show that there exists some n such that for all n greater than m greater than capital N, then the absolute value of Sn minus S sub m is less than epsilon, right? Well, for any n and m with n greater than m, we have, let's write out what this absolute value of Sn minus Sm is. So this is going to be the absolute value of, so Sn is the sum from I equals 1 to n of negative 1 to the I plus 1 a sub I minus the sum from I equals 1 to m of negative 1 to the I plus 1 a sub I. So this is just going to be this absolute value of the sum from n plus 1, from m plus 1 to n of negative 1 to the I plus 1 a sub I. Okay, now there's slightly annoying notation because you don't know, I mean, depending on what m and n are, you might have a coefficient of negative 1 in front of the AIs, right? So one way to handle this is to break this up into several cases. So for instance, you could use case 1. Well, what is our n going to be? I mean, I think we should take, now there's a bit of hindsight in this. You could initially take n to be large enough so that a sub n is less than epsilon, right? I mean, the idea is, if you go back to the picture, it kind of makes sense that if you take n large enough that a sub n is less than epsilon, then the differences will be less than epsilon. But let's just write that down. So pick n large enough that, now I'm actually gonna use epsilon over 2. So such that for all little n greater than capital N, a sub n is less than epsilon over 2. And we'll see why in the proof. Okay, so case 1, I'm going to look at cases depending on m and n being even or odd. So suppose that m and n are even. Okay, Well, then your S sub n minus S sub m in absolute value is the absolute value of A sub m plus 1 minus A sub m plus 2 plus dot 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 plus. Now since m is even, right, m plus 1 is odd, and so there's no negative 1 in front. There's no minus sign in front of the A sub m plus 1, but there is a minus sign in front of the A sub n. Okay, so you're going to get plus dot 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 plus A sub n minus 1 minus A sub n. That's how the series ends. Now this, we can group up these even number of terms together, and now each of these differences is greater than or equal to 0, and so this is just going to be A sub n plus 1 minus A sub n plus 2 plus dot 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 plus A sub n minus 1 minus A sub n. Okay, and we showed already that by the lemma that this is less than or equal to A sub n plus 1. Well, since m and n are greater than, so I should write let n and m be greater than n with n greater than m. Okay, so we know by the lemma that this is less than or equal to A sub n plus 1, and that is less than epsilon. Okay? In fact, it's less than epsilon over 2, but it's certainly less than epsilon. Now, case 2 is if m and n are odd. Okay, well, that's the same idea. Do we see why? Because then this S sub n minus S sub m, okay, you're going to have pretty much the same thing, except you have negative 1 in front of the A sub m plus 1, and then it's plus A sub m plus 2, and then it's going to end in plus A sub n, right? And then you can factor out a negative 1, so an absolute value of A sub m plus 1 minus A sub m plus 2 plus dot 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 minus A sub n, and then we're at the same situation as before, so this is less than epsilon. Right? Because we know that this is, you just do the same argument. The same argument that's here. And notice where the lemma came in. So the lemma is very useful. Okay, case 3 is if m is even and n is odd. So, I mean, all these different cases, the argument is the same. It's just that I have different cases just to make the notation, just because of the minus signs, right? So just to make it easier to handle the minus signs. So the absolute value of Sn minus Sm, in this case, is going to be the absolute value of A sub n plus 1 minus dot 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 plus A sub n. And, okay, here, I want to replace it with the previous case. I want to reduce this to the previous case. So now I use the trick of using the triangle inequality. This is less than or equal to A sub n plus 1 minus dot 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 minus A sub n minus 1 plus the absolute value of A sub n, right? By the triangle inequality. And now we use epsilon over 2. So this first one is less than epsilon over 2. And then the second one is less than epsilon over 2. And the sum is epsilon. So that's where I use the epsilon over 2 in case 3. And then in case 4, it's basically the same thing, right? If m is odd and n is even, then this absolute value is going to be the absolute value of negative A sub n plus 1 plus dot 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 minus A sub n, and then you just factor out the negative 1, and so it's the absolute value of A sub n plus 1 minus dot 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 plus A sub n, and then by the previous case this is less than epsilon. And that proves the alternating series test. So yeah, now this isn't the only proof, but it's one proof. You can probably make this simpler. In fact, if you look at this book by Ross, Elementary Analysis, they basically give the same proof but they break it up into cases if n minus m is even and if n minus m is odd. So they basically combine cases 1 and 2 into one case and then cases 3 and 4 into another case. But it's pretty much the same idea. Okay. And then the other thing I just want to mention is it's possible for the series to converge to A1, and it's possible for this series to converge to 0. So the series, so we're done with the proof. Series can converge to 0 or a sub 1 because you can have something like 1 minus 1 plus a half minus a half plus a third minus a third plus the fourth minus the fourth and so on. So what's going on here is that you start at 1, and then you go to 0, and then it's a half, and then 0, and a third, and 0, and a fourth, and 0, etc. And that series converges to 0, right? And it can also converge to A1. So if you have, let's see, 1 minus a half plus a half minus a third plus a third minus the fourth plus the fourth, etc. Then what's going on with this one is that you have 1, and then it goes to a half, and then it goes back to 1, and then 2/3 and 1, etc. So the series converges to 1, which is the first term. And I only want to mention this because in a book that I've looked at, they say that the series has to converge to a number strictly between 0 and A1, but that's not actually true. Okay, if you allow the terms to not be strictly decreasing, right? I mean, here the terms are decreasing, but not strictly decreasing. If they're strictly decreasing, then you can show that the series has to converge to a number between 0 and A1. But if it's just decreasing and not strictly decreasing, then it could converge to 0 or A1.